All right, so hi everyone. Let's get started. So welcome back from lunch. So as you know, this tutorial is about active learning from theory to practice. And I'm delighted to introduce our two speakers today. Our first tutorial speaker is Rob Nowak. Rob is a nose-push professor in engineering at the University of Wisconsin-Madison. He's one of the leaders of the field with a variety of interesting results at the intersection of signal processing, machine learning, optimization, and statistics, including seminal results in active learning, which is the topic of the tutorial today. Okay, and our second speaker is Steve Haneke. He is currently a research assistant professor at the Toyota Technological Institute in Chicago, and he works broadly in learning theory. And just like Rob, he has done a lot of seminal work on active learning. And so we're really, really excited to have both of them here today telling us about active learning. So, thank you.
Thank you, Nina, for that great introduction. It's a real pleasure to be here, and I'm really thrilled to see so many people out in the audience. I hope you can learn a lot during this tutorial, and we'll be around to answer questions and so forth. And I'll explain a little bit about the format in a minute here. I just wanted to mention that Steve and I have probably, and Nina for that matter, we've known each other since those two were graduate students. I was already a professor. I have to admit I'm a bit older. But I've known them for many years. We've worked together on organizing things and all sorts of stuff, so it's really nice to be together with them today. So this tutorial is going to be about active machine learning, and we're going to be largely focusing on the theory aspects of active learning, but I'm going to sprinkle in some of the practical applications and so forth as we go. And I'd also be happy to talk about some of that practical stuff in the breaks and during questions. So here's the outline for our tutorial. We're breaking it into 4 parts. The first part's going to be an introduction, and I'll do that. That'll be about the first half hour. Then Steve will take over for parts 2 and 3, which will be really diving into the theory of active learning and then discussing some advanced topics and open problems. And then I'm going to wrap up talking a little bit about non-parametric learning. This is going to be really kind of talking about some very, very ongoing work that I'm doing with some other folks too, so I hope you'll like that. And I'm noting at the bottom here that the slides for all of our parts here are available on that URL there. So I'll flash that up again at the end of my first part here, but if you want to follow along, the slides are online there. So what we're going to do is we'll do these 4 parts. During, maybe just given the size of the audience and so forth, it might make sense to take questions after each part. So after part 1, we'll take a little time for some questions. People can come up to the microphones again after parts 2, 3, and 4, and we'll do it like that. But if there's something really confusing or bothering you while I'm speaking, jump up to a mic and just say, hey, Rob, I don't get what you just said, and I'll try to field it right there on the spot. Does that sound like a good plan? Awesome. Okay, so I have to kind of be a little bit in control here. Normally when I give talks, I'm running around on the stage, moving around, pointing and things like that. But for this one, I have to stay here at least within facing this microphone. So I'm gonna, if I walk away and you're saying, Rob, we can't hear you anymore, yell out and tell me. So here's the conventional machine learning pipeline. The way it works is we have a large unlabeled data set. I'm showing it here in the case of an image classification problem. And what we do is we take a subsample of that very large unlabeled data set, and we ask a human to annotate some subset of it. So we get some human labels for things like dogs and boats and so forth. That gives us a smaller set of labeled data. We turn that over to a machine learning algorithm. It tries to then learn a predictive model mimicking the labeling process that this human expert is doing. So that's a conventional pipeline. And it's been really successful. These are just a few headlines. They're a few years old now, but they kind of capture all the excitement that has been going on in the machine learning area recently. And All Systems Go is actually the title of a Nature journal article talking about the success with the game playing system that AlphaGo. So all systems go, that's true, except when you kind of start to look under the hood. training these machine learning systems takes a huge amount of human effort in many cases. So millions of labeled images required, say, for ImageNet. For translation, these machines are learning to translate between languages by effectively reading more text than a human could ever learn in a lifetime. And in game playing, they're learning by playing more games than even my teenage son can stomach. So this is kind of a little bit of a confusing sort of situation. Machines are doing fantastic things, but they're not exactly learning the way humans are learning. And so there's a lot of interest and active research right now in trying to figure out how we can train machines with less labeled data and less human supervision. So the approach that we're going to talk about today specifically is active machine learning. And this picture sort of modifies that earlier pipeline to show you how active machine learning works. The idea is that rather than just taking a random subset of the unlabeled data and asking our human expert to label it, instead we're going to design an extra algorithmic component to the system, which is a data selection algorithm. And that data selection algorithm is going to be looking at all the unlabeled data as the machine is learning and judiciously selecting specific examples and asking the human expert to label those. The idea is basically the machine, as it's starting to build up a model of how to predict, it will flag confusing or cases or examples that it's very uncertain about and ask the human expert for help on those specific cases. So let me just kind of explain this idea with a motivating application here. This is something that I've worked on a bit with people in health and medicine. They're interested in developing machine learning systems that can predict disease outcomes from electronic health records. And this kind of closed loop, human in the loop, active learning process looks something like this. We have a large database of unlabeled electronic health records. We have a team or an individual human expert who provides labels to a machine learner. Labeling one electronic health record can take an expert several minutes to do, so it's a kind of expensive labeling process. And these experts are clinicians who typically get paid maybe $100, $200 an hour. So these labels are expensive. And the idea is that we're going to try to get that human expert or team of experts to label some subset of these electronic health records to teach the machine. And the active learning idea is that as the machine is learning to build up this model, it's going to automatically select specific unlabeled electronic health records that it wants the team of experts to label. So just kind of at a very high level, one of the most intuitive ways you might go about this active learning process is depicted in this figure here. So I'm just showing you two features from an electronic health record. Typically, we're looking more at like 10,000 different features or so, but to visualize it, we'll just look at two. So suppose we have electronic health record feature 1 and 2. Those are our horizontal and vertical axis. The gray dots are unlabeled electronic health records, and the red and blue dots are labeled ones. So we're labeling into two classes, say disease and no disease. And that dashed green line is the best linear classifier. So if we're thinking about which example to label next, the conventional machine learning pipeline would just pick one of the unlabeled examples at random and ask the human expert to label it. And that would give us a certain learning curve. So as we collect more labeled examples, of course, the error rate of our classifier will improve and go down. An active procedure would somehow, the machine would decide, well, which examples is it more uncertain about? And for example, a natural heuristic is to look at examples that are unlabeled and close to the current best decision boundary, like the orange one I've circled here. And the idea is that hopefully by strategically selecting those examples that are most confusing, this will help the machine quickly learn a good predictive rule and reduce the total amount of human supervision required in this learning task. So this is just some experimental data from some actual electronic health record cases. We have about 11,000 patients here, roughly 6,000 different features that we're looking at, and we're basically using an active version of logistic regression and also a passive version. And you can see that in this particular example, active learning was able to reduce the number of labeled examples needed to learn a good classifier by roughly 50%, about half as many required. So there are some significant gains that you can get, especially in cases where the human labeling is very, very expensive. So one of the things why you say, well, that's great, why don't we just always do active learning? Well, one of the reasons is that it's a little hard to implement these things. You're having sort of an online learning system as soon as you activize it. That becomes a much more intensive process. It's not like you just have a labeled data set and then you're going to take your favorite machine learning algorithm and apply it to that labeled data set. In active learning, collecting the data is part of the machine learning algorithm, and so that kind of gives you some more demanding system requirements. One of the ways that we've tried to allow researchers and practitioners to prototype active learning ideas is we built this open source software system that allows you to easily build up active learning systems. A lot of people have used it for many different applications. I'm just going to tell you about two of my favorite applications that I've been involved with where we've really seen active learning give helpful gains. One has been in active learning to optimize crowdsourcing in the New Yorker caption contest. And I'm not going to say much more about this, but if anybody wants to talk to me during the breaks or afterwards, I could tell you more about our collaboration with the New Yorker using active learning for crowdsourcing. And another one, this is a fun one that came out of one of my former students, Kevin Jameson's work. He decided he wanted to implement some active learning in the real world, so he built an app for the iPhone, which was a beer recommendation system, and basically it actively learns a user's preferences for beers quickly. And I just, again, the next system and this app are both free, so if you're interested in checking them out, no charge, so I'm not trying to milk you for money or anything here. All right. So what I want to do with the rest of this first part is just kind of go into a little bit of some of the basic principles of active learning. Some of the theory, just touching on it at a kind of high level, and then Steve's going to dive more into kind of more complex ideas in more detail. So to begin with, one of the things or ways I like to think about active learning is by distinguishing between what I call what and where information. So in the case of just learning a density, what information would be something like, what is the conditional probability of y given x? So here I'm showing you, say, y is the label, x is a feature. That's the conditional probability function. A where question is, where is this conditional probability function greater than 0? So that would be basically telling us what's the decision set for label equal, say, +1 instead of -1. Okay? So what information, in this case, what is this function versus where does this function have a certain property? Another what and where example is just in straight up density estimation. We could say we want to estimate the density of our data, x, or we could ask where is that density greater than some value epsilon. That's something you might want to do if you were doing clustering. And then finally, we could think of a function estimation case, like we want to estimate or learn what is the conditional expectation of y given x. That's a what question. A where question would be where is the maximum of that function. So for what value of x do we have a maximal reward? And this is basically the bandit setting. So it would be a certain location. So the point of this slide is just to kind of impress upon you that one of the most effective places for active learning is situations where you want to learn about where information. You want to localize something, a decision boundary, a maximum of a function, the support of a function, something like that. So all of these kinds of problems, clustering, bandits, and just general classification and prediction, have active learning versions. We're going to be focusing mainly on classification, and especially on binary classification, just to keep all of the math and so forth clear and as simple as possible. But a lot of the principles and ideas we'll be talking about can generalize to many, many different situations. Okay, so here is kind of a meta algorithm, if you will, for active learning. And it basically works like this. Suppose we have a collection of models or hypotheses. I'll call that script H. So that's the set of all models we're considering. If you want to keep something in your mind, think of all possible linear classifiers in some feature space. And then we're going to basically iterate over a kind of loop in which at each step we're going to first sample a random sample from the data set, from the unlabeled data set. We're going to then label only those examples that distinguish models in our current hypothesis class or version space. And then we're going to reduce that hypothesis class or version space by removing all models that are inconsistent with the labels we've received. And then we'll repeat this process until we've sort of winnowed things down to a small pool of very good models, or maybe just a single model, and output that. So here's how it looks in a picture. It's sort of this loop. So we have a model space. That's why I was calling H. We look at that model space, the structure of it, the geometric structure, what have you. We use that structure to decide how to select examples for labeling. We ask our human expert to label those. We get those labeled data, and then we use those labeled examples to prune or narrow our search over this model space, basically effectively reducing it. And again, this reduction is because we're throwing out models that are inconsistent with the labels we've received. So let me give you like the very simplest example of this. This would be learning a one-dimensional classifier. So what I'm showing you here, these dots are supposed to denote unlabeled examples. And you could imagine that if we labeled all of them, we could learn a nice linear classifier. So this would be, for example, if your blood pressure is above a certain level, then you probably have heart disease, and the red would indicate that. So we can contrast passive learning and active learning very easily, and I'll show you these two. So passive learning would just be randomly selecting unlabeled examples for labeling. And active learning, in this case, could be implemented just as a binary search or bisection procedure, where we keep trying to sample between the two closest oppositely labeled points. And you can see after a few samples, the binary search, the active procedure, has really nailed down where that decision boundary is, but the passive one is sort of very, very loose. It hasn't really figured out where to put that decision boundary. And in fact, just a little back of the envelope math shows you that the error of the passive learning method goes down like 1 over n, where n is the number of samples you've collected, versus the active method, binary search, is going down like 2 to the minus n. So we get an exponential speed up in how quickly we can learn from a small set of labeled examples. So this is kind of the classical starting point for trying to understand why active learning could help, and that's binary search. So then you can say, well, that's great. I learned about binary search in my freshman computer science class. Is that all there is to it? Well, there's a lot more to it. We're going to tell you about that. But the starting point for just saying how would we generalize binary search to more complicated situations is VC theory. And so let me just give you a kind of little bit of an introduction to this, and then Steve's going to talk a lot more about the theory of active learning in the next couple of parts. So suppose we're giving a set of training data x, y, so those are our labeled examples, and we want to learn a function f to predict y from x. So we're going to consider a possibly infinite set of hypotheses. I'll call it script f. I guess I was calling this script h before, so my apologies for changing the notation a little bit. But basically I'm saying suppose we have a big pool of hypotheses or models and they have a finite VC dimension, d. And so if you aren't familiar with VC theory, just think about D as the dimension of your feature space. That's what it would be in the case of a linear classifier, for example. So we have with that, for every F, for every model in this class, we can talk about its error rate, and we'll call that the risk. And so that's just the probability that f of x is not equal to y for a new pair xy. So the first thing you can do is you could say for any f, I could look at how well does it do on the training data. So this r hat of f is simply counting up how many mistakes do I make on my training set and then normalizing by n to get an average. We call this the empirical risk. And what VC theory does for us is it allows us to bound uniformly over all the models in our class the deviation or difference between the true probability of error or true risk and the empirical risk of each and every classifier f. And so this bound is saying that the maximum absolute difference between r and r hat for any f is less than or equal to 6 times the square root of that VC dimension d, and then there's a log factor there, log n over delta, divided by n. N is your sample size here, and delta is your confidence level. So we think of delta as some small number like 0.01, like 1%. We want to have 99% confidence that this bound holds. So how do we use something like this? So this is empirical risk minimization. I'm sure many of you are familiar with it, but bear with me. I just kind of want to go through this, and then I'll talk about how we activize this type of procedure. So empirical risk minimization, the goal is to select a hypothesis whose true error rate is within epsilon of the best we could achieve from any element of this class script f. So I'm going to talk about two different classifiers, f star, which is the true risk minimizer. It's the F in our class that actually minimizes the true probability of error, sort of the test error, if you will. F hat is the model that minimizes the empirical risk. That's something we can actually compute by just looking at the training data. And so since F hat minimizes the empirical risk, we know that the empirical risk of F hat has to be less than or equal to the empirical risk of F star. Okay, so that's kind of the key insight. And what it allows us to do is make a picture like this. So what I'm showing you is the empirical risk of F hat and F star, those are the blue dots, and then those confidence intervals are the confidence intervals we get from the VC inequality I showed you on the previous slide. So basically what that's saying is that the true risk of F hat is somewhere within the red bars around the R hat of F hat blue dot, and similarly for F star. So what does that do for us? So now we can sort of say, well, what do we know? We know that the true probability of error, the true error rate of F hat, with high probability is going to be less than or equal to that upper bound there, which is R hat of F hat plus that term coming from the VC inequality. And we also know that with high probability, the true error rate of F star is, at best, this R hat of F star plus or minus that bound coming from the VC inequality. So we know what those upper and lower limits are, and with high probability, those are where those true risks or true probabilities of error sit. And so what we can do now is we can just look at the difference. Okay, so the difference between those two bounds is just 12 times the square root of d log n over delta divided by n, the sample size. And what that means then is we can immediately identify how many training samples, how many labeled examples do we need in order to find an epsilon good classifier, where we're going to need this difference to be less than or equal to epsilon. So that's where the 12 times the square root of that business less than or equal to epsilon. And then we just invert that to solve for what should n be. And we find that n should be something like d log 1 over epsilon, or d log 1 over delta divided by epsilon squared. So what is that telling us? It's saying that if you're in a higher dimensional feature space or a larger VC class, or higher VC dimension, you're going to need more training data. It also says that if you want to push epsilon down, if you want to get closer and closer to that true best classifier within that class, you're also going to have to pay a price in how many labeled examples you need. And Steve's going to be elaborating on all this as we go forward. So let me just show you how this might look in pictures then. So what I'm doing here is I'm showing you empirical risks of a bunch of different classifiers, say. Each blue dot is the empirical risk, and the red bars, again, are those confidence intervals coming from the VC inequality. So we could order them like this, from lowest empirical risk to highest empirical risk. And what happens as we collect more and more training data, we'll shrink these confidence intervals, because remember, those VC bounds are going down like 1 over the square root of n, or proportional to that. And we'll get to some point like this if we've got enough training data, and at that point we can clearly see that with high confidence, model 1 is better than all the other models. And that's the idea of empirical risk minimization. You could keep going until you get this epsilon good model, or you could keep going if you have a finite set of models until one's clearly better than all the others, like I'm showing here. So what's the issue? The issue is that empirical risk minimization may be wasting labeled examples. And why would that be? So let's kind of back up to where we started. Let's collect some more data, shrink those confidence intervals, and suppose we're at this stage right here. Now, what could I glean from this picture? Well, if I had this picture, I can see that at this point, we know that hypothesis 1, or model 1, has to be better, or at least with high probability, is better than model 3 and all the others beyond model 3, right? And so we could actually remove that from further consideration at this point, and remove all the others. And we basically have boiled things down at this point to just a race between who's better, model 1 or 2, okay? So rather than continually asking for random examples at this point, we're going to kind of strategically select samples. We're going to only require labels for examples where hypotheses or models 1 and 2 label an example differently, where they disagree. And so this is the idea of disagreement-based learning. Steve is the world expert on this topic, and he's going to be talking a lot about it. But the idea is that now what the machine's going to do is it's going to say, okay, now I know. I just have to worry, is 1 or 2 better, model 1 or 2. I'm going to ask my human expert. I'm going to search through my data set of unlabeled examples, find examples where models 1 and 2 predict different output labels, and I'm going to ask the human expert to label those. Those are the ones that I'm confused about, me being the machine in this little story. So let me show you how that might look, and this is based on some of Nina's work, actually. How would you do this disagreement-based active learning in the case of a linear classifier? So what we're going to do here is consider points or unlabeled examples sprinkled uniformly on the unit ball in this picture, and we're going to focus on linear classifiers that pass through the origin or the center of this ball. So that's what one of the classifiers looks like. We don't know which one it is, so it could be in any orientation. So now what we're going to do, we're going to follow this empirical risk minimization idea. We're going to take a bunch of examples, draw them at random from our pool of unlabeled cases, ask our human expert to label them, and say we get these red and blue dots. So now what does that mean? It means that we know that the only linear classifiers that could be consistent with these labeled examples are the ones I've shown here. Okay? All the others we can rule out because they'd start to misclassify things. So what we're going to do then is we're going to focus now on this region where new examples might distinguish among those remaining hypotheses. This is the region of disagreement. We're going to now look at it. The machine will go and look at a large set of unlabeled examples remaining in that data set. But it's not going to label all of them. It's only going to label ones in the green region, in the disagreement region. So it's going to say, forget about all those, just label those two, and update your hypothesis. So we improve it a little bit. And to improve it, rather than having to label a bunch of examples, we focused our sampling and only labeled two here. And so that's the idea of disagreement-based learning. And basically, what you can say about that is kind of this sort of general type of result. And again, Steve's going to go into a lot more in a moment. But if we assume that our Bayes classifier, the optimal classifier, for our problem, F star, is in this VC class with dimension D. And we have some nice distribution. For example, the label noise is bounded. I don't want to get too much into these details. We can talk about it later if you like. But we're going to assume those two nice things, and we're going to let epsilon denote the difference between the error rate of F hat and the error rate of the best Bayes classifier, F star. So if we were in this kind of situation and we use the normal passive learning machine pipeline, then our error after n samples would be roughly like d over n. The dimension of our problem, the VC dimension, or the dimension of the feature space, just in a simple linear classifier problem, and that's what we call the parametric rate, d over n. If we're active, though, the error goes down much faster. It goes down exponentially fast, just like it did in that binary search example. It goes down like e to the minus some constant c, n over d. And so we get this exponential speed up in how quickly we can learn a good classifier or good prediction rule in this case. Okay? So that's what I wanted to say in this first part as a means of introduction. This is just, again, an outline of how we're going to proceed. Steve's going to take the next 2 half hours, so about 1 hour, to talk about the theory of active learning, some advanced topics after that. We'll probably take a little bit of a break between part 2 and 3 in case people just need to stretch their legs. And then in part 4, I'll talk about some ongoing work in the area of non-parametric active learning. And again, the URL for the slides is there at the bottom. You can follow along if you like, or download the slides at your convenience. So with that introduction, I'll stop here and I'll take questions if there are any, and I'll ask Steve to come up and he can start setting up while we're doing that.
Thanks for the presentation. It was really, really instructive. My question was about what if you have neural nets that are very powerful, so your VC dimensionality becomes very high? Would the same type of arguments apply?
So if you have a super high VC dimension, so in principle, as long as you're in a finite VC class, the sorts of things I talked about would still apply. But of course, they might become practically a little bit meaningless because, again, you're going to need at least as many labeled examples as that VC dimension. So if the VC dimension is extremely high, either you have a ton of labeled examples, either passively or actively, or you don't. And so that is a kind of a fundamental issue. Because large VC classes are just so expressive, right? They could kind of represent many, many complicated functions. Of course, you would expect it to take a lot more effort to learn such functions. I'm going to, in the last part of the talk, cover non-parametric and also sort of the over-parameterized setting, where we're always talking about basically more dimensions than we have training data. There we kind of have to depart from the usual statistical learning theory approach and VC theory and so forth and pursue other types of approaches. And so I'll be touching on that at the end, but that's very kind of nascent work it's just starting now. So it's a great question, but we'll be covering some of that, and hopefully if you have more questions along those lines, just ask me again. Yeah.
Okay, great. Rob gave, of course, this wonderful introduction to active learning as a topic and the theory of active learning and sort of the beginnings of why in special cases you can have a theory of active learning, a theoretically sound approach to active learning, and also some ideas about why maybe there was a general theory of active learning as well. What I'm going to be talking about in the second part here is indeed a general theory of active learning in more detail, general descriptions of algorithms and descriptions of the number of labels that are sufficient to achieve guarantees on the error rate expressed in terms of complexity measures. I'll say that the theory I'm going to be describing here referring to the question that was asked, I'm going to be expressing everything in terms of the VC dimension. That's mainly just for simplicity. Many of these results would also generalize to things like covering number. You could express them in terms of things like covering numbers and even localized covering numbers. And that would actually also address many things that aren't covered by bounds expressed in terms of VC dimension. But for simplicity, we'll stick with VC dimension throughout. Okay, and I'll mention that this segment, this second part of the tutorial, is covered very thoroughly in a monograph that I wrote a few years back, Theory of Disagreement-Based Active Learning. It is freely downloadable off my website, or if you want a bound version, I think you can purchase it off the publisher's website. Okay, so Rob introduced Hoeffding's inequality and a uniform version of Hoeffding's inequality. And for the purpose of stating sort of the tightest results that we can get in disagreement-based active learning, I'm going to need something just slightly tighter than that. So this is what's sometimes called Bernstein's inequality. Basically, it's just like Hoeffding's inequality. So if you have any two classifiers, the difference of their risks is bounded by the difference of their empirical risks plus a term that's like, looks like the Hoeffding bound, right? The square root of a log 1 over delta over m, except we're now multiplying inside by the fraction of the data on which the two classifiers disagree with each other. And we're just talking about binary classifiers. So this is saying one of them is 0, or sorry, let's say plus minus 1. So one of them is plus, one of them is minus. Okay. So that's a Bernstein's inequality, and just like with Hoeffding, you can get a uniform version of this. And here we're saying for a given hypothesis class, with high probability, for any two classifiers in the hypothesis class, the same inequality holds, except now we've multiplied by a VC dimension, and we've changed the log factors a little bit. Okay, and we're going to be expressing algorithms in terms of this. We're going to be using this to design algorithms. Right, so just so I can sort of reduce clutter on the slides, I'm actually going to use a sort of a simplified version of it, which is technically not accurate, but basically I'm shaving off constants and log factors and lower ordered terms just to reduce the clutter. It's sort of a conceptualization of the important parts of the uniform Bernstein inequality, and so this down here is what I'm actually going to be using. But just keep in mind that if you want to make these things formal, you really do have to take into account these the constants and the logs and lower order terms. Okay. So with all of that background, let's now dive into the general theory of disagreement-based active learning. So first I'll just maybe rehash in a formal notation what Rob was already defined. The region of disagreement of a set of classifiers H is just the set of points such that there exist two classifiers in H that disagree on the label of that point. Okay, it's a very simple notion. It's a region of the instance space. And with that definition, we have here a definition of the classic disagreement-based active learning algorithm, the A squared or agnostic active algorithm from Balkin, Bakel, Zimmer, and Langford. So this is a sort of a slimmed down version of the algorithm. So basically what you do on each round, you get some number of unlabeled samples. Let's say on round T, you take 2 to the T unlabeled samples. And we'll go ahead and just, here, I'll just do it in pictures at the same time. So we'll go ahead and query everything that's in the region of disagreement. Let's say initially everything is in the region. And then we'll minimize the number of mistakes. We'll find some classifier in H that minimizes the number of mistakes on that data. And then we'll actually look at all the other functions in H, let's say this one, and if they make a lot more mistakes than the f hat minimizer, then we actually just remove them from H. We throw them away. So like maybe this other curve that I've drawn makes a lot more mistakes, so I go ahead and throw it away. Maybe this one also, go ahead and throw it away. So what's left is a smaller set. We've sort of pruned the set H down to a smaller set of candidate hypotheses, and the region of disagreement of that set is potentially smaller. And then we iterate. We then draw more unlabeled samples. We just query the ones that are in the region of disagreement. Again, find some f hat minimizer of the number of mistakes there. If there's some other classifiers in H that make a lot more mistakes, we throw them away. And so H is getting smaller, and the region of disagreement is getting smaller, hopefully. And we do this for a number of rounds until some stopping criterion. OK, so what's the point of all this? Why are we doing, like this step in particular is, sort of looks like Bernstein's inequality, so why are we doing that? So the point of it is that if at the beginning of a round, the best, let's say f star is the best classifier in the hypothesis class, if it's still in the hypothesis class at the beginning, or in the version space, or the pruned down hypothesis class, then because all the classifiers in H at the beginning of a round agree outside of the region of disagreement, if f star is the best classifier overall, then it's still the best classifier conditioned on the region of disagreement. So it still has the smallest risk under the conditional distribution given the region of disagreement. So if we sort of plug that into the reasoning from Bernstein's inequality, what you're getting here is that the empirical risk, the excess empirical risk of f star is bounded by its excess risk under the conditional distribution given the region of disagreement, because that's what Q is sampled from, plus this sort of Bernstein-looking term, this sort of term from Bernstein's inequality. And then, as I just said, f star is still the minimizer under the conditional given the region of disagreement, so that first difference is at most 0. And so what you get to conclude is that f star is never removed. So if f star is in there at the beginning of the round, then given that Bernstein's inequality holds, it's still going to be in there at the end of the round. So this algorithm is sort of preserving this invariant that you never remove the best classifier from the hypothesis class. Right. So it's definitely doing something reasonable in that sense. And then we can ask, well, then how many labels does it use in order to get a guarantee on the excess error rate? And for this, we're going to need to introduce some additional notions of complexity, and this is where this notion of the disagreement coefficient comes in. So I'll define the disagreement coefficient. There's several different parts to it. The first part is this ball of radius r. So this is an L1 ball, essentially. So you take the ball centered at f star of radius r is just the set of classifiers in H such that the probability that they disagree with f star in a random point is at most r. And then the region of disagreement of that ball is just as usual. It's the set of points such that there exist two classifiers in the ball that disagree on the label of that point. So then to define the disagreement coefficient, you take the ball of radius r centered at f star. You calculate the region of disagreement of that ball. You calculate the probability mass in the region of disagreement, divide by r, and take the supremum over r. Okay, so that's the definition of the disagreement coefficient. I'll state some guarantees in terms of it, but first maybe let's go through some examples just to make sure everybody follows the definition. So the first example might be thresholds on the real line. This is sort of the simplest example. If you have, let's say, a uniform distribution between 0 and 1, and the set of classifiers are thresholds, so there's some point t such that everything to the right is labeled plus, everything to the left is labeled minus. Okay, so then there's some t star that corresponds to the f star optimal function. And any threshold that is bigger than t star plus r is definitely not in the ball of radius r because it has distance further than r, and anything less than t star minus r is definitely not contained in the ball. So that's the ball. It's the set of classifiers that are have their threshold between t star minus r and t star plus r. Okay, so and then the region of disagreement of that set of classifiers is just that same segment. The probability mass there is 2r, divide by r, so the disagreement coefficient is 2. So for thresholds, under this uniform distribution, the disagreement coefficient is just 2. Okay. To go up to a higher dimensional setting, let's consider, let's say, a uniform distribution on the surface of a ball of a sphere in n dimensions, say centered at the origin, and let's talk about the set of linear separators that pass through the origin, so homogeneous linear separators. So f star would be some separator like this, and the other separators in the ball of radius r would be sort of just like f star except tilted a little bit, just a slightly different angle, where the probability mass in that wedge between the two is at most r. And then if you think about all of the classifiers that are just like f star except tilted a little bit, the region of disagreement that they form is this sort of fixed width slab around f star. And if you actually sort of do the geometry, the width of that slab is going to be proportional to r. And it turns out that the probability mass contained in a region, a slab of of width r is roughly square root of the dimension times r. So if you divide that by r, you find out the disagreement coefficient for this case is roughly the square root of the dimension. Okay, so these are some examples to show that this is a quantity that can be calculated. Indeed, it has been calculated for quite a few different scenarios. And I'll mention a few general things a little bit later. But first, let's get to stating the results. Okay, so I'll start with a simple case, bounded noise. Rob mentioned this, sometimes called Massart noise. So this is an assumption on the type of noise that we're dealing with. And we'll look at two different assumptions in this segment of the talk. So under bounded noise, what we're assuming is that there's some beta, so that it's strictly less than 1/2, such that for every point, the probability that the label is different from f star's label, given that point, it's at most beta. So this is saying that there's some bias toward f star's label at every point. Okay, so this is bounded noise, and the number of samples, the number of labeled samples needed for passive learning, it's known to be about d over epsilon to get the error rate to be at most the error rate of f star plus epsilon. And for active learning, the guarantee here is VC dimension times theta log 1 over epsilon. Okay, so if theta is small, this is actually an exponential improvement in the dependence on epsilon. Another way to view that is it's a rate of convergence in terms of the number of labels. It'd be d over n for passive. It would be like e to the minus n over d theta for active. So again, if theta is small, that's an exponential rate. Okay. I'll just very quickly go through some high level of how that proof works. So for any given round, recall that all of the classifiers in H agree on all the points that weren't queried, on all the points that are in outside of the set Q. And so that means that actually in step 4, basically if you were to dump all of the samples that weren't queried back into the data set, it wouldn't change anything in step 4. Okay, so you would still basically be evaluating Bernstein's inequality, but now with all of the data. And so basically the guarantee that that gives you is that after step 4, the only classifiers that are left around have their excess risk bounded by roughly this square root of the distance to f star, d over 2 to the t. And then we're going to use the bounded noise condition. And this condition turns out to imply that the distance between the two classifiers that shows up inside that square root, it's bounded by a quantity proportional to the excess risk. So you can sort of plug in the excess risk inside of that square root and solve a little quadratic equation. And what you get out is that at the end of each round, the classifiers that survive have an excess risk that's bounded by like d over 2 to the t. And so you know that like roughly log d over epsilon rounds will suffice to give you that epsilon excess risk. Okay. And you can also use this bounded noise condition in combination with that guarantee to say that, to give you a bound on how many queries we made. Well, what it implies is that when you enter the round, H is contained within a ball of radius, like roughly d over 2 to the t minus 1, because that's the guarantee left from the previous round. And so then the number of queries is like roughly the probability in the region of disagreement of that ball, or upper bounded by it anyway, times the number of samples. And then so you just go ahead and evaluate that, and it comes out to, you make roughly theta times d queries on each round. Okay, so if you just sum up over that log d over epsilon rounds, you're going to get roughly theta d log d over epsilon as your total number of queries. Okay, so that was the bounded noise case. We can also look at weaker assumptions. So bounded noise actually makes some assumptions on how the probability of y given x behaves. We can also just look at the general case. We have an arbitrary distribution on x and y. And let's just denote, this is called the agnostic case. So let's just denote by beta the risk of the best classifier in the class. And then we can get this epsilon xx risk guarantee. With passive learning, it turns out you require about d times beta over epsilon squared labeled samples. And with active learning, again with the same algorithm, d times theta beta squared over epsilon squared. So what the difference between these two bounds is we've squared the beta. So we got an improvement in proportional to the error rate of the best classifier in the class, but we also multiplied by theta. Okay, so this is an improvement if theta is small and if the error rate of the best classifier is small. Okay. The proof runs essentially similar, and so I'm just going to maybe skip this for the sake of time. Okay, so as I said, there have been some studies of when is theta small, and we have some understanding of various general conditions in addition to many examples where it's been calculated. So for instance, if we're working with linear separators and the distribution of X has a density, and the F star separator passes through the interior of the support of the density. Turns out then theta is bounded, meaning it's not a function of the epsilon. Even if you don't have that second condition, even if you're just in the case where the density function, where the distribution of X has a density with respect to the Lebesgue measure, then at least you can guarantee that theta is little o 1 over epsilon. And it turns out that that's sufficient to guarantee some benefits of the active learning algorithm compared to passive. And then there are some more general conditions that for general function classes H. There's some work by Friedman from Colt 2009 showing if your hypothesis class is in some sense smoothly parametrized and you have some regularity conditions on the density of the X distribution, and you have some other technical conditions. So the functions are specified as sort of real valued, thresholded real valued functions, and they cross the decision, they cross the threshold at a certain rate, and things of this sort. Then the disagreement coefficient is going to be roughly proportional to the number of parameters in that smooth parameterization of the function class. I'll refer you to the original work for all of what the technical conditions are. And I'll just mention there are lots more examples and general conditions explored in that monograph from 2014. Okay. A few things remaining that I should talk about. One is I've so far left this stopping criterion in the active learning algorithm sort of vague. It really just depends on what context you're in. You're using this as to what stopping criterion you want to use. You could run this as an anytime algorithm, right? So if you want a classifier Friday at 4 p.m., you can just run it, and whatever the F hat it got on the previous round, it's going to be it's going to have those guarantees in terms of however many label queries it's made up to that time. You could set a label budget if you only can afford a certain number of labels, and it'll just run up until it makes that many queries. And again, you'll get a guarantee on that F hat in terms of what the label budget is. If you have a bounded amount of unlabeled data, of course, you can just run until you run out of unlabeled data, right? So on each round, it's using some number of unlabeled samples. If you run out of unlabeled samples, it doesn't really make sense to sort of cycle through this, the unlabeled data again or something like that. So that's another way that you can you sort of have to stop if you run out of unlabeled data. Another thing is that this algorithm and this generally disagreement-based active learning algorithms have this property of being self-verifying. And what that means is if you have an epsilon that you're trying to achieve, and so you know what excess error rate you're aiming for, you could just, you could evaluate this Bernstein inequality bound after each round, and it will sort of tell you whether you've gotten there yet or not. You can check whether your guaranteed excess error rate is at most epsilon after each round. So that's another way that you can set a stopping criterion. Okay. I'll mention also there is a simplification of this algorithm that makes a lot of practical sense. And this is based on work from Daniel Su and other co-authors over the years. Basically, it would be nice if you can implement this as a reduction to empirical risk minimization. And that has practical implications because empirical risk minimization can be difficult, can be challenging to run in practice, but you could just maybe plug in a different algorithm there, a different passive learning algorithm, and sort of still get a reasonable behavior in your algorithm. So here's a strategy that does that, does this reduction. Basically, sample points now just one at a time. And for each X that you sample, these are unlabeled points from the pool, for each label Y, constrain the label to be Y and then minimize the number of mistakes. So in binary classification, you're going to end up with two classifiers, one that definitely labels X as plus and then minimizes the number of mistakes, and another that definitely labels X as minus and minimizes the number of mistakes. And then with those two classifiers, just do this sort of Bernstein check. Is one of them much worse than the other? Basically, if the empirical error rates are very close to each other, then go ahead and request a label for X and add it to the data set. Otherwise, just skip over it, because we can sort of conclude that one of them is definitely worse than the other, so we know, we can kind of infer what F star's label is there. And again, I'm simplifying things a little bit, but not too much. This is a very nice, simple way to do effectively the same thing as these disagreement-based algorithms like A squared. And in fact, this will achieve roughly the same sample complexity as A squared. And the convenience here is that, as I said, this step, this 2, can be, this is an empirical risk minimization step. Okay, so technically there's a constraint there, but you can implement a constraint by just sort of putting in many copies of that example in the data set. And so you can just run empirical risk minimization. Okay, basically what you would do in practice, as I said, empirical risk minimization can be challenging to run. So let's just use a different passive learning algorithm there. And that's kind of one way to make these algorithms practical, is express it as this kind of reduction and then plug in a different learning algorithm. And in particular, so in the general case, if you plug in any passive learning algorithm there, maybe you'll lose the theoretical guarantees. But in some cases, you can still maintain some guarantees. So in particular, if you consider a passive learning algorithm that minimizes what we call a surrogate loss, just a relaxation of the 0-1 loss, hinge loss or squared loss, exponential loss. These are some popular losses, right? So now you have some function class that has real valued functions, and then basically you can minimize this surrogate loss function in that step instead of the 0-1 loss. And that's an algorithm that often can be run efficiently. And if you make some additional assumptions, so if you have this bounded noise and then some additional fairly strong assumptions, actually, on how the hypothesis class and loss function and distribution all sort of work together well, then you can still get this kind of guarantee that you get excess error rate under the 0-1 loss at most epsilon using a number of labels that's still like theta d log 1 over epsilon. And there are various other kinds of results that you can also express. Okay. And then I'll just conclude with one other modification, one other variant of this that is definitely worth mentioning. We've been talking about strategies that have like a set, and they'll query if the point is in the set. But you can also talk about strategies that set a probability of querying. And this gets into this importance-weighted active learning idea. So the idea there is on each round, you get this x. And now let's just set a probability, let's say p sub x, that you query that point. And then you flip a coin with that probability as its bias. If it lands heads, you query. If it lands tails, you don't. But if you do query the label, add it to the data set, but add it with a weight 1 over p, or 1 over p sub x. Okay. And the reason you do this is because the weighted empirical risk with those weights on the loss ends up being an unbiased estimator of the actual risk. And that's a very general statement. So no matter how you set these p sub x's, you're going to get an unbiased estimator of the empirical risk. You don't want to set them too small if you want to get, because there's some issues with variance and so on. But basically any choice of setting these px probabilities is fine. Maybe just don't make it too small. And that gives you some flexibility to plug in various ideas, various heuristics for designing active learning algorithms. And out of that, you'll get still some kind of a safety guarantee because you're dealing with an unbiased estimator of the risk. And I'll mention it's still possible to recover the disagreement-based active learning just by plugging in a sort of Bernstein indicator function for the PX value. So you sort of don't really lose something in terms of theoretical guarantees by expressing things this way, but you do gain a little bit of flexibility. And for that reason, this has been used actually in practical contexts. And right, and of course, yeah, at the end, we are running an empirical risk minimization step, but you could use, again, any passive learning algorithm there in practice. There is an approximate implementation of this strategy in the Vopel-Wabbit software library. It's maintained by Langford and cohorts. Okay. So that's the conclusion of the second part. We will get into other techniques beyond disagreement-based active learning in the third part. But I'm happy to take any questions right now. And otherwise, we will be taking a short, maybe 5-minute break between. So yeah, if there are any questions, please step up to a microphone.
So the second part, the algorithms had sampling just 1x, but in the first algorithm, you were sampling 2 to the tx, where
yes.
t is the iteration. So can you comment on the practicality of that and what is the trade-off between the number of samples? And it seems very extreme that one is exponential and the other one is just 1.
Right. Okay. So I'll give you 2 answers for this. One, from a theory perspective, the sampling in batches of exponentially increasing size gave us actually a simplification of the proof. The proof for sampling 1 at a time is a bit messier. Because we were sampling 2 to the t, actually in that proof, we ended up querying about d times theta on each iteration. And that's kind of a nice number because you can add it up a logarithmic number of rounds. And yeah, so there's a lot of simplification in the proof by having this exponential increase in the unlabeled data. From a practical perspective, there may actually be some reason to want larger batch sizes because, of course, you have some team of labelers, and if you give them more at once, they can label pretty fast, actually. If it's 1 at a time, then they're sort of waiting on the algorithm to give them the next query. Yeah, batches make sense in practice in many contexts also. But it is kind of nice to have a simple algorithm that just has 1 at a time also. So there's some... yeah.
Okay. Can I ask a question? So my question is there any no minimax lower bound regarding the label complexity of this problem? And if there is any minimax lower bound, so how is the performance of the algorithm that you just introduced compare with the minimax lower bound in terms of the label complexity? Thank you.
Yeah, it's a great question. We're actually going to talk a bit about lower bounds in the next segment. The lower bound, I'll say the lower bound for agnostic learning doesn't have the disagreement coefficient in it. And this is actually an open problem about whether you can generally remove that. And I'll get into a lot more detail about that in the next segment. In the bounded noise case, it's, yeah, it can sometimes be loose, but there's actually a known tight bound for the bounded noise case. Which unfortunately, I won't have time to cover here, but if you're interested, you can feel free to talk to me offline. But yeah, we'll talk about a tight bound for the distribution-free analysis of the bounded noise case. But even in the distribution-dependent case, we know of a tight bound, and we can talk. So
my question is also related to the batch setting. In my experience, batch setting is quite complicated usually because you need some kind of diversity term or something that tells you which batch samples to select, because just taking the n best or whatever based on a certain criterion usually doesn't lead to enough diversity in the samples. Do you have any take on good criteria for batch selection?
Right, so this approach is not actually doing anything with, we don't actually need anything to do with diversity in this approach. So we just have this notion of disagreement. Yeah, it doesn't sort of come up in this context. I think it will come up maybe in Rob's fourth part when we talk about, he's going to mention a little bit about cluster-based active learning, and then definitely there's some diversity that comes into play. But in this context, yeah, that's not really modeled. It might be implicit in there somewhere, but it's not really explicitly modeled. You have a question?
Yeah, with the same amount of data points, does active learning and passive learning like converge in the end, or it's doing better, I guess?
Converge?
Like if I do active learning, but use the same amount of data points as I would do with passive learning, would I give the same like classifier?
You're saying the same number of unlabeled data points?
Yes.
I don't think you get the exact same classifier just because of okay, you might be able to prove, like, with some high probability that it would be the exact same classifier, actually. But that some of that might depend on how you break ties in your empirical risk minimization and things like that. Okay. So what you would have to show is that on each round, you're not just keeping F star, you're also keeping the global empirical risk minimization, the global empirical risk minimizer, which I think you do with high probability. But that would be something that comes out of the analysis, not necessarily a guarantee. Okay,
thanks.
Hi. So I have a question about the choice of epsilon, since the bounds that you use to define the region of disagreement seem to depend on epsilon. It seems like the algorithm is not a priori independent to like your choice of epsilon. So how does your choice of epsilon affect like how quickly the algorithm will eventually reduce the size of the hypothesis?
Right. So this gets back actually to, and I have the slide here, the stopping criterion. So you know, if you use the stopping criteria that don't involve epsilon, then there's no epsilon showing up in the algorithm. It's just the guarantee there is just saying, if I happen to have that many labels, if I happen to have queried that many labels, then I'll have this excess risk guarantee at most epsilon. But you can also express it just in terms of how many labels did I query. You can get a bound. Basically, just solve that, set n equal to that and solve for n, and that would give you the bound on exactly, I don't know, yeah, like this, right? So here we've also expressed things in terms of the number of labels that we queried on the right-hand side. Right, so if you didn't have epsilon, if you don't want to set an epsilon, then you can just run the algorithm up to whatever stopping criterion you want.
Oh, I see. Okay. Thank you.
Okay. So maybe we'll just start on into the next part. These were all good questions. Okay, so we've covered sort of the basic theory that a lot of the literature is based on. What we're going to get into in this third part is right, essentially a sampler platter of different various ways that people have proposed to get a little bit better than disagreement-based active learning. So it's known that it's disagreement-based active learning. So it's a popular technique in the theory literature because it's simple. It has a very simple complexity measure that you can calculate very easily for a lot of spaces. And it's robust to noise. And for those reasons, it's sort of a lot of papers build on that. But if you're more careful in the way that you approach the problem, you can get improvements over it. As I say, it's known that it's not always optimal. And so we'll talk about some of those here. The first, I may not get to all these topics, but the first we'll talk about is sub-region-based active learning. So the idea here, and this is from Zhang and Chaudhuri, but it builds on a lot of earlier work, and there's a whole line of work on what's called margin-based active learning, and we'll talk about that also. Okay, so this is the basic A-squared algorithm that we've just talked about. And the idea in sub-region-based active learning instead of taking the whole region of disagreement, let's take a subregion. Let's take a smaller set that has some guarantee that for any two classifiers that are left in the hypothesis class, the probability that they disagree on a point that's outside of that region is at most some epsilon prime. Okay, so they don't disagree too much outside of the region. Now, of course, we could just take this R sub epsilon prime to be the region of disagreement, and then they never disagree outside the region. But if you're careful, you can sometimes choose a smaller set and get some benefits out of that. And yet, if you pick this epsilon prime carefully, you can still get this guarantee that after you run it for some number of rounds, you're going to get excess error rate at most epsilon. In particular, for bounded noise, if you run this algorithm with epsilon prime, it's like d times 2 to the minus t, something like that, you'll end up still having this algorithm will still have that property of preserving f star in the hypothesis class and get a label complexity guarantee. Okay, so then we can quantify the sample complexity of this algorithm, right, with this, again, just replacing the region of disagreement with this subregion. And basically what I've written here is just like the disagreement coefficient, except we replaced the region of disagreement with this sort of subregion of disagreement, of the region of disagreement. And here we'll get basically the same kind of guarantee that we got for disagreement-based active learning, except we replace the disagreement coefficient with this new quantity, this phi. And that's for bounded noise. There's also a version for agnostic learning. The quantity is defined a little bit differently, where the beta, the error rate of the best classifier, sort of shows up inside of the radius and in the denominator. But otherwise, it's defined essentially the same way. And here again, we recover basically the same guarantee that disagreement-based active learning had, except we replace the disagreement coefficient with this other quantity. And because this subregion is potentially smaller than the region of disagreement, this complexity measure is often, well, it can be smaller than the disagreement coefficient, and we'll look at some cases where it's actually quantifiably smaller. Okay. So this is one idea for getting beyond to an improvement over disagreement-based active learning. So the question comes up then, of course, how do you pick this region? As I say, you could just pick it to be the region of disagreement, but that's kind of, okay, you just recover exactly the A-squared algorithm. You can choose it empirically, and this is an interesting idea from Zheng and Choudhury. They sort of set up this kind of linear program approach to use the data set to figure out which points to include in the region and which ones not to. And that's a general approach, but maybe you have to do some more work to get a priori guarantees out of that. But then another approach, which goes into literature that actually predates this paper, is using some nice structure in the hypothesis class and distribution. And this is where we get into, for linear separators, for example, this notion of margin-based active learning. Okay, so I'll just describe that in some detail here. So remember, let's talk about, for simplicity, a uniform distribution on a d-dimensional sphere. Let's take f star to be the red separator here, and the blue separator is some other, well, let's call them w star and w, so linear separators. Okay, so then what we can do is project. So we have two weight vectors, right? Two linear separators. And let's project onto the span of the two weight vectors. Okay, so what you end up with is this, right, if you project on the span of two vectors, you're going to get a two-dimensional space, and that distribution projects onto a disk in the two-dimensional space. And the region where the two classifiers disagree with each other is just this green region. And the interesting thing that happens when you project from a high-dimensional space to a two-dimensional space, if you started with a uniform distribution on a sphere, most of that probability mass is going to end up kind of around the middle. You're right. It's not going to be like all over the place like a uniform. It's actually the density function of the projected distribution drops off exponentially as you move away from the center. And what that means is you can draw, like, let's say, a region like this, and you'll still capture most of the probability mass. In particular, you'll capture most of the probability mass where the two classifiers disagree with each other. So you can put like a slab around one of the two separators, and you'll, if you take that, let's say the two separators were within distance r of each other. If you take that slab of width like roughly r over square root d, you're still going to capture most of the probability mass where the two disagree. And so basically the idea is, well, let's do that for all of the separators. And what you end up with, if you think about this back in the higher dimensional space, is you're just talking about taking a slab around the actual W star separator in the higher dimensional space. And so let's take that as our region. It's just a slab of width roughly r over square root d. Okay, so as I mentioned in the previous part, the region of disagreement is actually a slab of width roughly r. So here we've reduced the width of the slab to like r over square root d. And yet the little regions, these little purple regions that we clipped off, didn't add up to very much probability mass. So we could still maintain some kind of bound on how much disagreement there is outside of this smaller slab. And then it turns out if you have a slab of a given width in d-dimensional space, the probability mass in that slab is like roughly square root d times the width of the slab. So, so here we have a slab of width r over square root d. If you divide by, if you multiply by square root d, you get r. And just to throw that definition back up, then so that's the probability mass in the numerator. If you divide by r, then turns out this thing is constant. So this complexity measure is bounded by a constant in the case of this uniform distribution on a sphere if you take the region in this margin-based way. As opposed to, in comparison, the disagreement coefficient, if you recall, was square root d. So we're actually getting an improvement. So you plug that into the theorems. In this case, what we're getting out of this subregion-based technique is a number of labels like d log 1 over epsilon was sufficient, whereas for the a-squared algorithm, we were getting that times the disagreement coefficient, right? So d to the 3/2 log 1 over epsilon. Both of these are improvements over passive in terms of the dependence on epsilon. Passive learning had a d over epsilon dependence, right, so in the case of disagreement-based active learning, it came at the cost of a square root d factor, whereas in the this margin-based, the subregion-based approach, we're not even losing any dependence on d. Okay. Since we're talking about margin-based, I should mention there's this, as I said, there's this literature that even predates the general idea of subregion-based active learning, and that's the margin-based active learning. And there's a simple way to describe margin-based active learning that is worth going through just because it's a very nice, simple description. So that kind of concentration around, like within a slab around the separator, that wasn't just true for W star, that's true for any separator. So in particular, we could do it for the W hat separator, for instance. Where, say, on each round, we have some W hat. And let's say, so here's the algorithm. And believe it or not, this is kind of roughly a similar, it's sort of a relaxation of that exact algorithm that I had on the previous slide. So on each round, you're taking a number of samples. And let's just query the samples that are in some slab around our current guess, our current W hat. And then, and then we update W hat by minimizing the empirical risk and maybe subject to a constraint that we don't wander too far. So if you, in step 3, there's a constraint that we don't move too far on each round. But basically, we're minimizing the empirical risk on each round. Okay? And that's the algorithm. Then we just repeat that. So we have a margin of a certain size, 2 to the minus t over square root d, and we sample within that margin and do this minimization step to update the separator. And under bounded noise, we would get this d log 1 over epsilon sample complexity, just like what I mentioned on the previous slide. And so this is classic work from Balkan, Broder, and Zhang. Since there has been a whole sequence of papers that extend this to other distributions, like isotropic log concave distributions and S concave distributions now. So there's a family of distributions where this will work. It has to do with when you project to 2 dimensions, do you get that nice concentration of the probability mass inside of a slab? So distributions that have that property will kind of work with this technique. Okay, so since I have margin-based active learning up on the slides, I want to mention as a kind of an aside, a cool result that came out of this literature. This is work from Awasti, Balkan, and Long. Basically, if you just make a slight change to that algorithm so that in the minimization step, you use a surrogate loss, you can get a very nice property. So in particular, what they'll use is the hinge loss, but they actually increase, on each round, they're actually going to increase the slope a little bit, well, exponentially. So on each round, they increase the slope of the hinge loss. And just by making that change, right, so we talked about surrogate losses before, and you could do all of that. But here, they're actually changing the surrogate loss from one round to the next. And what this does is really cool because you end up with, you're getting these label complexity guarantees. So this algorithm still works without any additional assumptions, just the same assumptions that we had, right? So that unlike what I mentioned about surrogate losses before, where you had to make additional assumptions, here there's no additional assumptions with this use of this surrogate loss. And it's, because it's a convex loss, your running time is polynomial. So this is actually an efficient algorithm for learning under bounded noise with these distributional constraints. And in the agnostic case, you can also get a result. It's also in polynomial time, but a little bit weaker because now you can only get just a multiplicative factor of the optimal risk. But what's remarkable here is this is actually the first algorithm, passive or active, to be able to achieve these kinds of polynomial time learning guarantees for these kinds of noise models. And that's, so it's interesting that the first algorithm that has that guarantee came out of the active learning, thinking about things in terms of active learning. And this will also work for other distributions, isotropic log concave distributions, for instance. Okay. For the sake of time, I'm going to skip over the next part and just get into the next topic here, distribution-free analysis. Okay, so everything that we've talked about with the disagreement coefficient and the subregion, and the complexity measure for the subregion, and the thing that I skipped over, shattering-based active learning, these are distribution-dependent quantifications. So if you remember, for the linear separators, we were talking about uniform distributions and things like that. Okay. You could ask, can we do a sample complexity analysis without a distribution dependence? And we can. And the complexity measure here is actually quite simple. This is the key complexity measure. It's called the star number. It's the largest integer k, such that there are k+1 hypotheses. Let's call them h0 through hk. They're in the hypothesis class h. And there are k points, let's call them x1 to xk, such that for any I, hi disagrees with h0 only on xi. Okay. So to say that sort of in a hand-wavy way, what we're talking about is having k points such that there's some labeling of those points where I can flip any of their labels while holding the other ones fixed. Okay? So that's the star number. It's never smaller than the VC dimension, but it can be larger, arbitrarily larger. Okay, so I'll just do a couple of examples just so everyone's clear on the definition. Let's talk about our simplest problem again, the threshold classifiers. So here, again, there's some, everything to the right of some t is plus, and then I can choose t, and that tells me which classifier I'm using. So here the star number is 2. Okay, so if you took 2 points, you can have an h0 threshold between the two, and then I could move to the right and flip that label without changing the other one. I can move to the left and flip that label without changing the other one. So you can, the star number, so you can convince yourself that you wouldn't be able to do this with 3 points. Okay. For linear separators in 2 dimensions or higher, already it's infinite. Okay, so here what you could imagine is having points on a circle. H0 is some separator that doesn't it just labels all of those points minus, let's say. And then each HI just chops off that XI point, just that one point off the circle. Okay, so I can flip any one of the labels. If the H0 labels them all minus, I can label any one of them plus while keeping the other ones all minus. Okay, and you can do that with any number of points. So the star number for linear separators is infinite. For interval classifiers where it's like a segment, it's infinite there also for a very similar reason. If you're talking about interval classifiers between 0 and 1 and you constrain their width to be W, turns out that's an intermediate case where the star number is like 1 over W. Okay, so this is the star number. Why do we care about it? Well, one reason we care about it is the complexity measures that I mentioned in the previous parts. If you maximize them over the choice of the distribution on X and the F star function, you get exactly the star number. Actually, what you get is the minimum of the star number and 1 over epsilon. So let's just denote that by S sub epsilon to simplify some expressions. Okay. And this is actually not unique to those complexity measures. There have been many other techniques in active learning proposed over the years, and I won't have time to talk about all of them, but each one comes with some interesting complexity measure, and it turns out in every case, if you maximize them over the distribution and F star function, you get the star number. So it's kind of an interesting unification of all these various distribution-dependent theories. So for immediate corollary of this is that under bounded noise, you can get by with a number of labels that's like SD log 1 over epsilon, or in the agnostic case, you can get by with a number of labels that's like SD beta squared over epsilon squared. Actually, with the beta in this S, that we didn't show that, but that you can also do that. This S sub beta instead of S sub epsilon. Okay. And these are achieved by A squared. Then I'll say that there's actually a different algorithm that gets a little bit better than this. And so this is sort of moving beyond disagreement-based active learning. There's an algorithm that under bounded noise just gets S sub epsilon over D times log 1 over epsilon. So we sort of if S is bounded, we shaved off a factor of D in that label complexity. And this is actually nearly matching a lower bound. So in fact, there's a sense in which this is not an improvable guarantee. So this is kind of optimal in the distribution-free analysis under bounded noise. And for agnostic, we don't know. So actually, the guarantee that was stated over here for disagreement-based active learning, the S times D beta squared over epsilon squared, that's still the best that we know for agnostic learning. The lower bound is like that, but without the S, so basically D beta squared over epsilon squared, plus a term that's essentially the bounded noise sample complexity. So that's a special case of agnostic noise. It's not known if you can get an upper bound that essentially matches that. And in particular, what I wrote here, this open question, can you get D times beta squared over epsilon squared plus the bounded noise sample complexity upper bound? That's not known. Incidentally, I have offered a prize for this. If any of you can prove this is true, I'm willing to give you $500. So, yeah, okay. Great. Okay, so that's some guarantees you can get. Let's talk about how to get these guarantees. In the case of bounded noise, so we'll talk about an algorithm that makes this improvement for bounded noise and solves a special case of this agnostic question. Okay, so the way that this happens is basically what has disagreement-based active learning been good at? it's been good at sort of finding interesting things happening with the f-star function. Places where there's a lot of interesting stuff like decision boundaries and things like that. Finding decision boundaries, finding places where you want to focus your queries because there's a lot of complexity in the f-star function. But there's another thing that you can do with active learning that disagreement-based active learning doesn't do at all, and that's adapting to heterogeneity in the noise, meaning that there's some places that are very noisy and some places that are less noisy, and you might want to adjust how many queries you make in each of those types of regions. Okay, and we're going to talk about here, very briefly, an algorithm that is able to do that. So basically, we're going to imagine having some active learning algorithm that expects to get exactly f-star labels. It expects to get true labels for the f-star function. And then what we'll have is a subroutine tick-tock that sort of denoises noisy labels in order to feed into that. OK, so again, very briefly, if we have, let's denote eta of x is the expected value of y given x. So y here is plus minus 1 labeled. So this is a value that goes from -1 to +1. And if we suppose, let's say f-star is the global optimal function now, and this is actually some additional assumption. So instead of just being the best function in the class, which we'll assume it's the best function in the class, but we'll also assume that it's equal to the sign of the regression function, the sign of expected value of y given x. Which is that's the Bayes optimal function. So now what this tick-tock subroutine, this sort of denoising routine is going to do is essentially query, if you give it a point x, you say, I want to know f-star's label at x. So now it's going to query, let's say it can either query at x or maybe very nearby. And there's some analysis you can do to show that there's a sense of metric. There's a kind of a metric where very nearby has an importance in VC classes. So if you query very nearby to this point x, you can get labels that are essentially like independent draws from y given x. And you can use them to try to figure out, you're sort of doing a sequential hypothesis test to sort of figure out, maybe with some reasoning involving like Hoeffding's inequality, for instance, to figure out whether the eta value, the expected value of y given x, is bigger than 0 or less than 0. If it's bigger than 0, I'm going to infer that this is a positive. If it's less than 0, I'm going to infer that this is a negative and return that label. But, and here's the important thing, if I run, I'm going to set a cutoff, this tau. And if I have made tau queries and I still haven't figured out, using Hoeffding arguments, whether the sign of expected value of y given x is plus or minus, I'm going to give up. I don't return anything. So in the end, we're going to be training an algorithm on just labels that were returned from this. Just the examples that this tick-tock tiered cutoff in a test for the optimal classification. That's the acronym. Just the labels that tick-tock returns. Okay, so if we think about what's the effect of that, the ones that we don't return, those are the ones where it's hard to figure out whether it's above 0 or minus or below 0. Those are the very noisy points. So this is essentially biasing our queries toward less noisy points. And this has a double advantage. One, the less noisy points are the points that we actually care about. If you write down what is the excess risk at a point, condition on a point, it's the indicator that the two functions disagree times the absolute value of eta. Okay, so a large eta, that's a less noisy point, is a point that we care about more in the excess risk. It's a point that labeling it opposite f star matters more to the risk. And the other thing is if the points that have lower value of eta are also easier to determine the f star value. Right? So the number of queries needed to determine f star using this Hoeffding argument is like 1 over eta squared. Okay, so we get this double advantage of we use less queries and we focus on the points that matter more. Okay, and the output of this is that guarantee that I mentioned for bounded noise. This algorithm gets that s log 1 over epsilon. And in the agnostic case, with the one additional assumption that f star is this global best function, then we're getting exactly the conjecture that I mentioned on the previous slide. the d times beta squared over epsilon squared plus the bounded noise complexity. Okay, and this is optimal, unimprovable. Okay. And this gives us some motivation of a couple of principles for active learning. We want to query in dense regions where f hat could disagree a lot with f star. That's the kind of thing that disagreement-based active learning does. And then the second part, we want to query in regions that have low noise because those points matter more and they're easier. Okay, and I will skip over this for the sake of time. So the conclusion, there are many proposals for going beyond disagreement-based active learning, and each exhibits some improvements in certain cases, but yet we still don't know what is the optimal agnostic active learning algorithm, and in particular, we don't know how to get this kind of a guarantee on the sample complexity for agnostic learning without any additional assumptions. Okay, with that, I will conclude the second part. Happy to take questions if we have just a brief moment while Rob comes up and sets it. Are there any questions you can approach?
Okay, great. Well, thanks, Steve, for a really great deep dive into some of the theory of active learning. What I'm going to suggest is I'm going to give this last part 4. It's going to be a little bit more kind of open-ended, a little less theory, a little bit more about maybe some of the important problems that could be out there and really meaningful to applications too. And then when I wrap up with that, what I thought we could do is Steve can also come back up. We can field all sorts of questions at that point. People can also head off to the coffee break, but Steve and I are going to hang around. People want to come up and discuss things as well. So what I want to talk about in this last little segment here is what you might call non-parametric active learning. And I'll say a bit about what I mean by that as we go here. So a lot of the active learning theory methods we've heard about so far are based on taking some class of models, usually something like a finite VC class, and then using the structure and geometry of that model class and the geometry and structure of the data set to kind of adaptively and selectively decide which labels to take to narrow down the pool of viable models. And so let's just think about how that would work. If we were just learning a linear classifier, again, this is the EHR type of problem I had up before. In this particular case, the best linear classifier for this set of labeled data would be the green line I show you here. It's not a perfect linear classifier. It's missing that little clump of 3 blue labeled examples up in the top, but we can't really accommodate those with a linear classifier. Right? So this is kind of the situation that's almost going to always happen in a real world problem. Your models probably aren't going to be rich enough and flexible enough to cover everything you might encounter. So what can happen? What might go wrong with active learning here? Well, it could be, if you're not using one of the very careful algorithms that Steve described, you might actually end up converging to a suboptimal solution. And this can happen, especially if you're doing one of these very aggressive, greedy types of active learning algorithms that we talked about earlier in the first part. And so the inductive bias or model bias associated with the class of models we're considering means that in situations where the data are really messy and the optimal Bayes classifier is not in that class, then the standard active learning algorithms might not really work much better than passive learning, and worse yet, if you're not being really careful, they could actually converge to suboptimal solutions and do worse than passive learning in the long run. And so that's a concern. Why is it a concern? Well, if you listen to some of the futurists, we may be worshiping an AI god by, I guess, 2042. And we certainly want to make sure that this AI god is not converging to a suboptimal position. So I don't think I can underscore the importance of getting this right more strongly. Okay, so this is a term, it was actually the title of a paper by Sanjoy Dasgupta that I really like, two faces of active learning. And basically he was saying, like, here are the two things that we're generally trying to do. Either we want to label examples close to the decision boundary, we've talked a lot about that and saw a lot of pictures about that, or you might want to find clusters in your unlabeled data set and label representatives from each cluster, and that's sort of kind of riffing on the heuristic or a possibility that maybe clusters of data reflect homogeneous sets of labeled examples. And so our goal in what I'll talk about now is to think about how we could use non-parametric or also over-parameterized models to avoid bias and design active learning algorithms that exploit intrinsic structure in the data, like what I'm showing you here. So I'm going to first just talk about two motivational papers that I really like. The first one is also by Dasgupta and Xu, and this is a paper on hierarchical active clustering for active learning. So the idea works like this. So we're going to first of all take our large pool of unlabeled data and we're going to hierarchically cluster it using some clustering criterion. And I'm not going to go into what that criterion could be. It could just be your favorite unsupervised clustering algorithm. So let's say we do that. We keep kind of splitting up our data, doing this sort of hierarchical clustering. So we end up with a cluster tree like this. So that's step one. Now, step two, what we're going to do is we're going to go back up to the root of this tree first. We're going to label some examples. And we see that if we label this subset, some are red, some are blue. So this cluster itself is inhomogeneous. It has some reds, it has some blues. So we're going to have to go down further in the tree. We're going to go to the next level. And I guess, I'm not sure which, yeah, on the left there you see we have a kind of a mixed bag. We have some reds and blues again, but over on the right we have the samples that we labeled are all blue. And so we use this sort of to test. Are these clusters looking like all the labels might be the same within the cluster? And so on the right there we think, yeah, probably not. So we'll stop there. That looks fairly homogeneous based on that sample. And we can make this into a formal test. But on the left, we have to keep going. We're going to sample again there. And so that's the idea. You build up this tree in an unsupervised fashion, and then you proceed down through the tree, repeating this kind of test for homogeneity in the labels within each cluster. And you stop when you get to some place where you think, yes, I'm confident that it's fairly homogeneous. And the cool thing about this is that if you had a tree like this, and if it were possible to prune the cluster tree to M leaves so that the labels in each of those M clusters are relatively pure, then only order M labeled examples will suffice to accurately label the entire data set. So you could almost think of this as kind of like an active annotation problem. We have a huge pool of unlabeled examples. We'd love to just have it fully labeled. That would be fantastic. We could use that for whatever machine learning purpose we like. And so this gives you a kind of interactive, adaptive way to try to annotate a very large data set. And if there's a lot of structure in that data set, in this case in the form of clusters, you're going to be able to do a good job with far fewer labels than labeling everything. So another paper that was really inspiring to me is this paper by Zhu, Lafferty, and Garamani. They called it Combining Active and Semi-Supervised Learning, and it sort of riffs on a similar idea. We're going to use kind of a graphical notion and try to exploit the structure and geometry of the unlabeled data set. So where you would start is you build a nearest neighbor graph, say, of your unlabeled data set. And then what you're going to do is use a prior probability model based on the graph structure, the graph Laplacian, and select examples in a sequential fashion to minimize the predicted risk under that prior probability model. And then once you've labeled some subset of them like this, what you can do is then propagate the labels to the rest of the graph using nearest neighbors or the graph Laplacian extension or whatever. And so this kind of graph theoretic semi-supervised learning kind of can exploit cluster structures, but it can also detect boundaries, and sort of has both of those faces of active learning are being exercised in a procedure like this. And it works pretty well in practice. This has some pretty impressive empirical results, but there's not a very well, there's no real theory to support how it's working. We don't have sample complexity bounds and things like that. So Jerry and I and one of my students went back to the drawing board a few years ago and tried to develop a little bit of theory to help explain the good performance of these types of methods. And we kind of developed a method you can think of as sort of like a binary search on the graph. And so the basic idea is you start off again with that unlabeled graph over your, or a graph over your unlabeled data set. You start randomly selecting nodes for labeling until you find at least one red example and one blue example. So for example here, now I have one red and 3 blue. And what you're going to do at this point is you're going to look at all of the paths through this graph between oppositely labeled examples. So in this case, there are 3 paths, one from each of the blue to the red. And then among those paths, you're going to select the shortest path. So this is the shortest path, this one. And you're going to ask for a label that roughly bisects that path between the red and blue example. You're going to repeat this process, just keep refining and bisecting the shortest path as you go, and eventually end up like a picture like this, where you've sort of disconnected parts of the graph from each other. Because once you have 2 oppositely labeled guys that are adjacent connected by an edge, you remove that edge. So you get a picture like this, then you can propagate the labels again using nearest neighbor or some other extension. And this has some really nice properties too. It turns out that if the cut set, so if you had a graph that had homogeneously labeled pieces, you look at the cut set. If that cut set has m edges, then about order m labeled examples suffice to accurately label the entire data set. So this again is sort of like this idea of active annotation. You have a very large unlabeled data set. You would love to have it totally labeled, but that's going to cost you a lot. So can I interactively go through that large labeled data set in a way that speeds up the ability to label it all accurately? So the last part of the talk and the tutorial here, I want to talk a little bit about how now we can take some of these ideas and move into, really contemporary machine learning frameworks like kernel methods and neural networks. The active learning based on the graphs and clusters are effective, but they kind of had this 2-stage process where first you build a graph or a partition over the unlabeled data set, and then you exploit the graph or cluster structure for active learning. And that doesn't really play well with things like neural networks and so forth. So we're interested in, can we develop similar procedures that can be applied directly to popular classifiers like kernel methods and neural networks? So this is really kind of just ongoing work, and I'll show you a little bit of our understanding of the problem, but I want to warn you that this is not a completely polished set of theory. So to begin with, I want to just remind everybody here, I think people have seen this because it's been controversial and also really stimulated a lot of rethinking in the machine learning community. And that is this conventional wisdom of the so-called bias variance trade-off. And the idea is that yes, if we use very, very complicated models, we can eventually drive that training error to 0. We can fit the training data exactly, but then that might generalize very poorly. And so that's what this kind of figure demonstrates, the classic U-shaped form of the test error. So if we start overfitting the training data, we might actually generalize very poorly. So this was basically how we thought about machine learning for decades. This is sort of at the root of a lot of statistical learning theory, including the VC analysis and all that. But what happened is people started experimenting, especially with deep neural networks, and they found kind of surprising contradictions to this picture. So for example, this is some work using inception on CFAR10, and basically this neural network has more parameters than we have training examples, so we can perfectly interpolate the training data. That's why you see the training error going to 0. So there's no bias. We fit exactly the training data, but also it doesn't kind of blow up. The generalization is also very good, or at least not getting worse as we overfit to the training data. And so deep nets are trained to perfectly fit training data, yet they still generalize well. And this has been an observation that people are starting to understand theoretically, and it really has been a big source of new research in machine learning. So this picture I like a lot. This is due to Belk and Shu and Ma and Mandel. It's what they call the double descent. Other people have also discussed this kind of behavior. So to the left, you see the conventional classical setting where we have fewer parameters than we have training examples, and we do see that U-shaped test error. That's what I'll call the classical regime. But if we move over, if we start looking at models that have more parameters than we have training points, then we move into this modern, what we could call the interpolating regime. And what can happen is that as we push beyond that sort of critical sampling level, where number of parameters equals number of training examples, we can actually see the test error decreasing. So even though we're interpolating and perfectly fitting the training data, which we can always do in principle as soon as we have as many parameters as we have training examples, if we keep pushing along on that complexity axis, we can drive the test error down. So that's kind of crazy and very surprising, but the idea is that we're not just looking at any interpolating model, we're looking at interpolators that are in some sense the smoothest of all functions that could interpolate a given set of training data. And so smoothness, subject to interpolation constraints, is a form of regularization or a form of Occam's razor. So this isn't just a kind of theory. These are some experiments that Belkin and his collaborators did. This is a neural network example, but similar real data examples happen with kernels and random features as well. But you see distinctly that W characteristic in the blue curve, which is the test error here. So it's definitely a real thing. It's definitely happening. And we're starting to understand why that is. And again, the idea is that we're going to interpolate, we're going to perfectly fit training data, but we're going to do it in a way using the smoothest possible function for within whatever architecture we're using. So, so now how do we use this? What does this say we should be thinking about in terms of active learning? And this, again, is somewhat speculation and kind of my initial thoughts on it, but I think it's kind of interesting, so I wanted to share it with you. So standard active learning theory methods are based on bounding test error in terms of training error, right? And that's what VC theory is all about. But if we're interpolating, then the training error is identically 0. And so whatever model we have, if we have multiple different deep neural networks or multiple kernel methods, we're always going to train them to fit the training data. So we need to kind of think about something other than just looking at that training error as a means of selecting good models. So what I'm going to talk about now are some preliminary results and experiments with kernel machines and neural networks. Kernel machines are single hidden layer neural networks, and I'm going to be focusing on just a single hidden layer case. Interpolation is going to be possible here if we're using, say, an infinite dimensional reproducing kernel Hilbert space, or if we have an over-parameterized neural network. And so I'm kind of showing you that here by giving you a sense that this hidden layer is very, very wide. And so the number of units in that hidden layer might be many more than the number of training examples, for example. So we have more weights in our model than we have training examples. So let's think about this for a second. I'm just going to show you some pictures in 1D to build up a little intuition. So suppose that I have these 6 labeled training examples, the reds and the blues. They're labeled +1 or -1. And then I'm showing you as those open circles, those are all the remaining unlabeled samples that I haven't received a label yet for. The black curve is this minimum norm interpolator of the given 6 initial training points. And now the question is, well, which point should we label next? So if we label any given point, I'm kind of sliding it around there, we have 2 possibilities. That new point will be labeled blue +1 or red -1. Okay, so which one should we take? So suppose we took an example here. I'm showing you in this kind of magenta color a point U. This is a new example that's in between 2 identically labeled examples. So you can see that this new point is selected to be between 2 of the red labeled points. And if I added that new point in, either I'm going to get a label of +1, and if I do, then I get the blue interpolation curve that I show on the top, or it will be labeled -1, red, and I get the red interpolation curve that you see below. And what you can kind of see here is that because that new point lies right in between 2 red labeled points, it's going to be pretty easy to interpolate. So it's easy to interpolate. That's what the red curve is showing. If I switch the label to blue, then it's going to be much more difficult to interpolate. That's what you see on top. So basically the wiggliness of the blue curve is saying it's difficult to interpolate, it's less smooth, whereas the red curve is very smooth, not much different than the original black curve, and it's much easier to interpolate. And so we can measure this in terms of a norm. The norm could be the norm in the RKHS space, or it could be the norm of the neural network weights, for example. If we instead look at a slightly different point, say we take a point that's in between two oppositely labeled examples, so this new point U that I'm showing you here now is in between a blue and red labeled example. Now what happens is no matter what we choose to label that guy, either blue or red, it's going to be difficult to interpolate because you're really kind of trying to squeeze them in between two oppositely labeled examples. So in either case, it's difficult to interpolate. The new interpolation function will be much more wiggly, less smooth, and we can measure this again in terms of the norm. So here is a heuristic then. I'm just going to propose a heuristic for how you might decide to select a new example. The selection of the next example to label is a U star that is the solution to this max-min problem. For any given point U, you're going to look at how wiggly would the new function be if I label it -1, and how wiggly would it be if I label it +1. And so I can measure that again with those norms, and I just pick the more convenient of those two labels. Whichever label seems to be easier to accommodate and interpolate. So that's what that min is saying. And then I max over all possible unlabeled examples. And so this is basically the intuition here is we're going to try to attack the most challenging points in the input space first to eliminate, hopefully, the need to label other easier examples later. And this is a very recent kind of tech report that's up on arXiv if you want to go to look at it. So what are the properties of this? That's just a heuristic. It kind of seems like, well, maybe, Rob, that seems kind of reasonable. What does it do? So here is that criterion again, and it kind of has some nice properties that you can actually verify analytically. First of all, the minimum norm labeling of a new example U is given by the sign of the current interpolator. So you really don't, all you have to do is say, well, does the current prediction say that should be labeled +or -1? And that's the right label to take then for that new example. It tends to select samples near the current decision boundary and closest to oppositely labeled examples. And what this together means is that in the case of a simple one-dimensional problem, it yields an optimal binary search. So it sort of reduces to things that we know are optimal. And I'll just show you that with this little movie. So this is an example where I have a multiple threshold problem in one dimension. It's just a synthetic example. But what happens is this max-min sampling criterion adaptively sort of goes in, locates a decision boundary, then moves on and finds another one. And what you can prove about it is that if I have n points more or less uniformly distributed on the unit interval, and there's a piecewise constant sort of labeling function like the blue thing I'm showing you here, then this kernel active learner will perfectly label all endpoints after only labeling k log n of them. So again, this is kind of like this idea of active or interactive annotation. We're going to start marching through our unlabeled data set, but we hope that we can accurately predict all the labels before we had to go and get a label for every single example. So here's what it looks like in 2D. It gets more difficult to analyze this kind of procedure in 2D, but if you run it, for example, on this case where I have just a two-dimensional decision boundary, what it does is it sort of initially does some random sampling. It finds a decision boundary, and then it kind of stitches along and traces it out. So it's really focusing on that decision boundary, and eventually it will learn it perfectly, and that will be the end of the process. So here's how it works. I'm just showing you now a few snapshots of the process through time there on the left. But it has its strengths and weaknesses. So what's the strength? The strength is if you look over at this graph comparing the learning rates, we basically get to a zero error very quickly. The training error goes to zero as soon as we found that full decision boundary. And so the red curve's dropping way below the blue curve here. Unfortunately, though, it looks a little weird over here. Initially, random sampling, passive learning, is doing a little bit better than this active learning procedure. And what's happening there is that the max-min criterion is really nailing just a fragment of the decision boundary, but not the entire decision boundary. And so that leaves a lot of uncovered space. So it sort of has this almost like phase change characteristic where once you've found the decision boundary, the error drops to zero, but before that, you're kind of missing a lot of the big picture. So that's the limitation. It can be a little bit myopically focused on learning the decision boundary, and it's not really sensitive to the distribution of the data, and that's another kind of issue. So we also study a different type of norm, just a variation, rather than using the kernel norm or the neural network weight norm, we could use a database norm. So here's the idea. So again, we have F will just denote our minimum norm interpolator of a given set of initial training examples. FU will be the, sorry about that. F superscript U will be the min norm interpolator if I add the point U. And then what we'll do is to choose which point to label next, we're going to look at which point and resulting interpolator sort of leads to the greatest change from the previous interpolator. But we're measuring that greatest change or the most significant amount of change with respect to the full pool of unlabeled training examples. So this has a lot of nice properties too. I'm showing you a comparison of the movies in this two-dimensional setting using the RKHS norm and this database norm. And what you can see is that the database norm strikes a balance between focusing on that boundary and then exploring more globally. Eventually, it really starts homing in on the decision boundary, but it's getting kind of a more accurate, large-scale picture of the problem at the expense of maybe not perfectly nailing down exactly where the decision boundary is. So here are just some snapshots over a number of labeled examples in this case here of the two different norm criteria. And again, what you see is, oops, maybe I didn't, sorry. I guess I may, what you can see is that basically both of these active methods are doing better than passive, but the error decay of the database criterion is much more graceful. It doesn't have this like sharp phase change. It starts improving on active learning right off the bat. So in practice, we've observed this kind of behavior works a bit better in application. Here's another cool feature of the database criterion. It actually has this sort of cluster-seeking nature. So this is, again, how it might cover both phases of active learning. The RKHS norm, or neural network weight norm, really is aiming to nail down decision boundaries, whereas the database criterion first makes sure it covers probability mass and covers the problem well. So it sort of finds roughly one representative from each of the clusters first. And I'm just going to wrap up with, again, I just want to caution you, this is all very preliminary, but we have been running experiments with MNIST and other things, and we see essentially the same story being borne out with real data. So here is an example comparing passive learning to the max-min criterion, the database criterion, and you see that we're doing driving the training error to zero very quickly using active learning compared to passive learning. That generalization or test error is stabilized. We're not really too worried that we're possibly overfitting, just the new story that's emerging about this interpolation regime. And then we also see that the max-min criterion initially does maybe a little bit worse than passive learning, but eventually catches up. And so I'm going to stop that there. I'm just going to say a couple of conclusions. So the theory and methods of active learning are really well developed in the classical statistical learning framework. The problem is that the classical theory may not be applicable in this over-parameterized regime that I was just talking about. And so we have this new framework based on minimum norm interpolation that shows some promise in theory and practice. And what I think is really exciting is there are a lot of opportunities for developing new theory, especially in conjunction with modern deep learning methods. And there's a big space for improvement in terms of developing new computationally efficient active learning algorithms. And so I think it's a great time to try to jump into the field. I just have the note of the slides there again. And I forgot to tell you before, and Steve was good to show these, but with each of these slides, we also have some recommended readings pointing you to some of our favorites in the literature. They're not comprehensive, but it certainly will give you a good set of starting points if you want to explore more on your own. So with that, I'll thank you all for listening. We'll take more questions. I'm going to invite Steve back up here, but it's been a real pleasure and an honor to address you today, and I hope this was valuable to you. Thanks.
Hey, so for those clustering-based methods for active learning where you're kind of automatically annotating the data based on the clusters, how does using those data to actually train a classifier compared to just using some sort of k-nearest neighbors method and just, using those labels automatically on like a test set?
You want me to? So the idea in the clustering methods, again, is to use some unsupervised learning to try to figure out, is there some interesting geometrical structure in your data? And that it sort of follows, both that and the graph-based learning methods follow the sort of semi-supervised idea, in that something about the structure and distribution of the unlabeled examples is giving you a little bit of a clue as to what the labeling might be, or at least where the labels might be similar to each other. So if I see an isolated cluster of examples, maybe those are all cats or all dogs. And so that's the kind of intuition behind those methods. So I wasn't quite clear exactly, I'm not sure if that's answering your question or if you, yep, is that? And so you do really want to kind of look at the geometry, maybe that those data are clustered, or maybe they're on some sort of low-dimensional manifold and high-dimensional feature space, and so that's sort of what we're trying to exploit in those methods. And they do work, well in many cases. Yeah.
In your last example, you had that classifier FU that depends on the new data point U, but how do you compute this without knowing the label of U?
Yeah, so if I go back to, for example, this new, maybe I'll say here, so F superscript U is the minimum norm interpolator adding the new point U. So there's, in binary classification, there'd be two options for that new data point, +1 or -1. We actually try to interpolate both cases. So we say, what if we made it plus, what if we made it minus? And then we say, which one of those two is the simpler function? And then we're going to go with that one as our sort of prediction of what the label should be. It's going to be the easiest one to interpolate, right? And so that's what F superscript U here denotes. It denotes with this sort of most, the easiest choice for what that label would be. Yeah, so you kind of guess ahead and take the easier of the two cases in binary classification. You could generalize that to multi-class too. Thanks.
Thank you for a great talk. And I think for the minimax, the argmax max-based sampling algorithm for the over-parameterized scheme, I think every example is about no noise setting, so where no label noise setting. And I think maybe that max-based scheme can be easily fooled by the label noise because it is somehow greedy. And so do you have any experiment about under the label noise setting?
Yeah, that's a great question. So the question is, this kind of max-min scheme is quite greedy. And if there's label noise, it could be noise seeking, it could easily get fooled, and so forth. And so that's a great point. But I'll just say, if we go all the way back to this idea of over-parameterized interpolating models, even if you have label noise, sometimes these can still be very, very good. I mean, if there's label noise, you can't predict noise, but maybe the best interpolator still generalizes about as well as something that tried to not interpolate the data. That's sort of what those double descent curves are telling us, and there's not a lot, but there's some theoretical work out there to help us understand and explain this phenomenon. So in what I propose for this new active learning framework, I'm just going to say, let's run with that idea of being over-parameterized and interpolating the training data. We know that is sometimes not such a bad thing to do, even if there is label noise. And so our goal is to essentially try to label everything in the training set, perfectly fit our model to the training data. And that's what we're doing in a lot of modern applications. And if you're, that might not always be the best thing. It's not to say that regularization and so forth can't help. But if we are going to try to operate in that interpolating over parameterized regime, then maybe this is a reasonable active learning strategy.
Hi.
So, thanks.
Hi. So it's very similar to the question asked before. Like if we have noisy data and over parameterized networks like deep networks, if we want to try something like a disagreement-based learning, how are we going to, like, what are some good ways to come up with good models, like, on the data we already have, which have enough diversity to have some disagreement?
Right, so yeah, the question is about running disagreement-based learning with over-parameterized models that can interpolate, right? I'm not sure that's wise. In fact, you would just query everything, right? Because you could label it in either way, and it wouldn't really affect your ability to fit the other data. So yeah, so disagreement-based learning in these over-parameterized cases that theory hasn't really been developed as to what's the right way to do it. I think that, I mean, and this has come out a lot, you know, the nature of the algorithm really matters in those cases where you have a lot of parameters, what algorithm you use, and so maybe there's some theory that could come out of if you're using a certain algorithm to minimize the empirical risk in it, maybe there's some way that you can still get something like disagreement-based learning to work. But that theory has not been developed yet.
Okay, thank you.
Hi. So for the kind of algorithm that Steve talked about, like the say-squared and the margin-based learning, slide-based learning, I was just wondering if there is any software easily available, so I could probably play with it and build some intuition.
Yes. If you get the slides, there's a name in there, the Vopel-Webbit library, which is available online, I think on GitHub somewhere. If you search for Vopel-Webbit, you'll find it. It's maintained by John Langford and his group.
Okay, thanks.
So it has a kind of a, with a bit of a heuristic in it, but it has a sort of an approximate version of a disagreement-based learning algorithm, the IWAL algorithm.
Hello, thank you for the tutorial. So I'm wondering about the minimum norm framework and the margin algorithm earlier you mentioned. Looks like it could be some connections between them, but I'm not quite sure. Would you mind sharing some insights there?
Yeah, I think your intuition is right. I think there are connections. You know, the first one that we were able to rigorously establish is the connection between that criterion and basically an optimal bisection procedure in one dimension, and how it relates to margin-based types of ideas in higher dimensional spaces is something we're trying to explore. I don't know that it's going to be super easy to come up with a nice, clean theory because it's such a general, flexible kind of approach, but certainly experimentally we see some correspondence between what we'd observe in a kind of margin-based sampling scheme and that max-min criterion. And I should also mention that the behavior I showed you in those two-dimensional types of examples is very, very reminiscent of what we see when we run the graph-based kind of active semi-supervised learning procedures, have a very similar kind of behavior. So I think an interesting area that I'd like to explore more are these connections between some of the well-developed theory and methods for active learning and something that you might be able to port over to deep learning systems and so forth, like the max-min criterion.
Thank you.
Hi. I have a very naive question. In active learning, we say that if we want to add more samples, we want to take the more complex samples, the one lying at the boundary. Now, in curriculum learning, we're saying that if we want to learn a better model, we should start only with the simple samples and then add progressively more complex samples. So at first sight, it seems a little bit contradictory. I was wondering how you would make sense out of that.
Maybe I'll take a quick stab at it, and then Steve can probably say more too. But there is an area called machine teaching, which is a little bit more in line with the idea of teaching a student. So if I have a learner and I know the model or an algorithm that they're using to learn with, then I could strategically develop a curriculum to help them learn in as few examples as possible. So the idea there is that the teacher, the supervisor, knows the algorithm the learner is running. And then knowing the algorithm that the learner is using tries to pick out good teaching examples. That's a little different than active learning, where the learner itself doesn't really know what it's trying to learn, but is still trying to somehow adaptively request help from a supervisor. So I don't know if you want to add anything to that, but machine teaching is sort of more similar to the problem you mentioned, which is related to but a little bit different from active learning, because essentially machine teaching means that the supervisor, the teacher, knows the learning algorithm that the learner is using, and that teacher is in charge of picking examples.
All right. In a sort of orthogonal direction, and possibly related to this, is that a lot of the techniques that I've mentioned also, that both of us mentioned, could also be used in conjunction with some model selection. So you could, for instance, learn the best linear separator using some agnostic active learning techniques, and then say, okay, if that's not a good fit yet, I can then get a larger model class, maybe quadratic curves, maybe some kind of neural net or something. So you can increase the complexity, and you can actually decide how complex of a model you need while doing active learning, and you can do it while sort of still being better than passive learning for the similar kind of model selection type of task. So there's some literature on that as well.